So what's the approach that we're going to take? Well, basically, we have a single degree of freedom undamped system. So this has obviously got damping in, but an undamped system will obviously would not have the C in, but you've got basically a differential equation, okay, where this is obviously the second derivative with respect to time. And we have a forcing function at the end, f of t, okay? F of t is the forcing function. And we've got this differential equation, and basically the math behind it is the same as you would use in mathematics when you've been given a differential equation and said find the solution. Well, we're doing exactly that, but obviously this is in the context of a vibration problem. So with an undamped system, obviously this is with a damped system with a damping. Let's first look at an undamped system where we've got where C is 0. The solution to this equation will follow this format, okay? Where CF is what's known as the complementary function, and PI stands for particular integral. And so it's made up of these two values added together. Now what's XCF? XCF is the solution to this function with no force, okay? So last week we covered, well the week before last, we covered undamped free response and damped free response. And so what you do for an undamped system is you take that undamped free response, and that is your XCF, okay? The free response is what XCF is. XPI, though, is what takes into account of the force, okay? And we'll go through how to solve this problem in quite a lot more detail, because XCF we know the solution to, okay? And so your complete response will be a component that's the free response plus the component that's due to the force, essentially, okay? And what happens is in a real damped system, XCF will slowly decay away to nothing, okay? And you'll be left with just the PI bit, because obviously XCF, as you know, a free response that's got damping. As you start the oscillation, it will oscillate, and then the oscillation will die out to nothing, okay? Whereas XPI will be left with you, okay? Because obviously that's the bit that's due to the force that's being applied, okay? But obviously in an undamped system, then XCF will remain with you as well. XCF is the complementary function, and XPI is the particular integral. Okay, and like I say, complementary function is the free response, and PI is due to the forcing function that's being applied. So in the case of an undamped system, the solution looks like this. Okay, we've seen this before, undamped. Okay, so you've got an amplitude times by cosine, and the cosine is with a frequency of omega naught, which is the natural frequency of the system. Okay, and you can also write that in terms of A1 and A2, which we covered last week, okay? The fact that these two things are equivalent. And you saw that in the tutorial as well. Okay, and then so obviously omega naught is root k upon m. A1 is A cosine phi, and here we've got A2 being minus A sine phi. In the case of a damped system, you've got this as your free response, okay? The only difference being this is now alpha, not phi, and you've got this decaying exponential in there as well, e to the power of minus zeta omega naught, and your frequency is now omega d. There should be a t there. Apologies. It's amazing how many times you go through a set of notes before the year starts, and you continue to spot problems. So this is on page. So on the top of page 36, okay, there should be a t after the omega d in that equation, okay? Apologies about that. So yeah, for a damped system, the solution looks like this, okay? And again, you can separate the A cosine blah 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 into a cosine and a sine term. And again, omega naught is root k upon m. Omega d is now a function of zeta and omega naught, and then A1 and A2 are the same things in terms of alpha now instead of phi. So XCF is easy, okay? You've done it all before. If you know you've got a damped system, then you've got this solution. If you've got an undamped system, then it's this solution, okay? Straightforward. Right, XPI. Now XPI, to find XPI, the particular integral, is it's quite a crude method of trial and error. What you do is you look at the force, okay, that's being applied. That'll be a certain function, and your particular integral is going to be of the same form of that forcing function, okay? And so I've got a little table here, and the table's in your notes. Basically, if your force is a constant term, then you make a trial solution, okay, that's a constant term, and you solve for what the unknown is. And here, constant term, I've called it C here, and what I do is I try a trial solution, and I've called it, and these Greek terms down here are all the things that we're going to try and work out. Okay, if it's a constant term, then I'm going to try a constant as my trial function, and we go through and solve it. You'll see that in a second. If it's a polynomial, so some function of time, okay, and that function can be written as a polynomial, then you try a polynomial of the same order. Okay, so if this is a t squared term, then obviously r is going to be t. Okay, but the alpha and the beta and the gamma and so on, you'll have to solve yourself. And lastly, if it's an exponential, then we make our trial function to be an exponential. And the reason I'm calling it a trial function is we test it out. Is this a solution? And if it is, what are these values of alpha and beta and gamma and all that sort of stuff? Okay, so we're going to go through and solve those things. So it's a trial function. And like I said, the choice of trial function will depend on what your forcing function is. Okay, so if your forcing function is a polynomial, then this is what we try. And if your forcing function is an exponential, then we try this one, okay? And so on and so forth. And basically we find these values, okay, based upon our differential equation, and then you can then solve for the whole problem. And you get a general solution, and then you apply initial conditions to get the exact solution.